Recording. Okay. So every time you break a bond, it requires an input of energy. Every time you form a bond, it releases energy. Oh, and now it's having a fit. Let's see. Oh, there we go. It's back. Okay. So in a reaction, if it requires more energy to break the reactant bonds than is given off by forming the product bonds, the reaction will be what? Endothermic. And if it requires less energy to break the reactant bonds than is given off by the forming the product bonds, then the reaction will be exothermic. So all it requires us to do is to take a look at our compounds, and we can say, okay, we've got, in this one, we are combusting some methane. All right, so we have CH4. So we have a carbon that has 4 bonds, and we break those apart, and we have the oxygens, each of which is double bonded to their oxygen partner. So we are breaking these bonds here, 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 here. So that's 4 of those get broken. And then 2 OO double bonds get broken, right? And then we have 4 OH bonds, and we have 2 CO double bonds. Thank you. You get to keep that. It's yours. So overall, in this particular case, it looks like making the new bonds gave out more energy, yes? Because we had to put energy in to get up here, and then we got energy out to get back down here. So my net change in energy is negative, yes? So the energy went up when we broke the bonds, it went down when the bonds were formed, and so overall it went down more than it went up, so net you have a decrease. Yes? It's considered, like, just call it potential energy for now. Okay? So if you imagine I've got these 2 magnets, right? And when I pull them apart, they're the higher energy. And if they come back together, they're at a lower energy. So it's exactly that process. It's just that if you're forming different bonds, then some of them are more stable than others, and so they will be at a lower potential energy. Yeah. It is the fact that the electrons in the outer shell would like to be close to the nucleus of other atoms. Yes. Yes. Exactly, exactly. If you think about an ionic compound, it's really easy to visualize because you have a positive ion and a negative ion. Boom, they want to come together. But it is similar. It is similar for covalent compounds. It's just that, you know, we're dealing with the outer shell electrons and the nucleus. Yeah? Yeah. Thank you. So in grade 12, when we draw our energy diagrams, we're no longer going to simply have them go like this or like this. We're going to have that bump in it where we break some bonds, and we had to put all those sorts of energy in, and then we have a decrease when we form bonds, okay, and the energy comes out. So this is what it's going to look like when we draw potential energy diagrams in grade 12, okay? Yes, so we have an endothermic reaction here. We had to break this much. And when we formed them, we got that much out again. So it took more energy to break them than we got back out. It's all good. Okay, yeah. I'll just staple them together that way for sure. So our net energy change then has to be positive because we put more in than we got out. Yes? And it's the same? It seems highly unlikely. I don't know. Not that it could be impossible, but highly unlikely, because it would mean that the energies of the bonds that are formed in the new compound are exactly equivalent in energy to the bonds from the old compounds. Yes? Well, let's take a look. So, what we're going to do, and we will be learning later on how to draw the Lewis structures. For now, they are drawn for you, okay? So we draw the Lewis structures for all the molecules. So we've got two NOCLs, and so we draw our NOCl, okay? We have NOs, so we draw NOs, and we have a Cl2, so we draw a Cl2. And what that means is we now know that in order to break the bonds, we didn't actually break the NO bond, yes? This bond here stays intact, yes? So we don't have to worry about that one. What we are breaking is we are breaking an NCl and another NCl. So we're breaking two NCl bonds, and we are forming one ClCl bond. Okie dokie. There are tables of bond enthalpies. So you will be given a table of bond enthalpies. And you'll look on the table of bond enthalpies, and you will find that an NCl bond is 200 kilojoules. That's the energy contained in an NCl bond. A ClCl bond has 243 kilojoules. So if we break two of those, it's going to be 2 times 200 kilojoules. Yes? And if we form one ClCl bond, then we release only 1 times its thing, which gives us 243 kilojoules. So this is the energy absorbed to break the bonds, right? Because bond breaking is always endothermic, right? And so that value is going to be positive. Does that make sense? Because we've broken those, that's a positive value. Now, we have formed bonds over here. And when we form bonds, that is exothermic. And that means that that energy change is negative. Okay? Now, how do we know what the overall change is? We simply add the two together. Yeah? So we would say we've got positive 400 plus negative 243 equals 157 positive kilojoules. And so since the overall delta H is positive, then the reaction was endothermic. So we would write this as, if we had to rewrite the equation, we would say I have 2 NOCl goes to 2NO plus Cl2. Where would I put the heat term? On the right or on the left? In the reactants or in the products? In an endothermic, the energy enters. Yes, it goes in the reactants. Endothermic, the energy enters. Yes? So over here is where we will put our heat term, and that will be 157 kilojoules. Is good? Yes. What determines the energy of bonds? It's going to depend on the size of the atom, because it's all going to come down to Coulomb's law, which we'll get into shortly. Coulomb's law looks like this. Force is equal to K, which is a constant, times Q, which is a charge, Q1, Q2, over R squared, and R is the distance. The greater the force between two charged particles, the harder it is going to be to break them, and the more enthalpy there is in that bond. Okay, so when we say bond enthalpy, we mean the potential energy stored in the bond. And so if you have something where you have a very strong force, then you're going to have a very high bond energy. If you have something where the attraction is very weak, then it's going to have a lower bond energy. It'll be easier to break that bond. So far, so good? Okay, this force is dependent upon the charge. As charge goes up, the force will go up. So let's say you had Na and Cl versus Mg and O2, or sorry, O2 minus. Which of those would have a stronger bond? Right? Because we have bigger charge, so the force is going to be greater, right? So, and similarly, if the distance between the particles is bigger, the force will be smaller. So we will look at this later. We don't know yet how to say, oh, which ion is bigger and which is smaller. But if you have a couple of big ions, they can't get, their centers can't get as close to each other as a couple of smaller ions. Okay, so this one would have a weaker force, and this one would have a stronger force. We'll go into the details of that later. That's how you know. Yes, sorry. Your homework is on the board, okay? 108.1. And the reason is that although they are super close together, You get a table of all the things, and we will actually spend more time on it than 5 minutes. Yeah? Yeah. It'll be, well, it's in this chapter. But, yeah, we'll do a quiz on like all the enthalpy and quantity terms, just all the enthalpy stuff, and everything extra. Yeah. Oh no, we'll come back to it. There's a whole thermochemistry unit. We'll be like, oh, and remember back in reactions when we did this? Yeah. Well, there's another way of calculating the entropy of the reaction. Oh. Right? This is one of several ways that you can figure out the change in entropy of a reaction.
So it'll be in the
yeah, thermochemistry. Yeah, so it'll be in this section and in the
okay.
Both.
Thank you.
선생님이 기다려줘.
Okay.